Mousetrap Car project by Michael
and Sammy.
This is our free body diagram. As you can see, the friction is to the left and the tension's to the right. The normal force and the gravitational force cancel out. This is our energy bar diagram. As you can see, when the car starts out, it starts out with all potential energy. Work is put into it when the lever uncoils the string, and then ends up with mostly kinetic energy and some potential. This is our data table. We calculated the average time as 4.7295 seconds, the average distance as 7.863 meters, and the average velocity as 1.649 meters per second. This is our position time graph. As you can see, as the time increases, so does the distance. This is our velocity time graph. You can see that the velocity remains constant with the increasing time, and we found a best line of fit for the acceleration. This is our acceleration graph. You can see that the acceleration remains constant, and we calculated our acceleration as 0.6371 meters per second.
Squared.
Squared.
This is our calculations. In order to find out the potential elastic energy, you need the equation 0.5 K times delta X. To find the kinetic energy, you need 1/2 mass velocity squared. Our equation for our problem, since there's potential energy at the end, is 1/2 K delta X equals 1/2 mv squared plus 1/2 K delta X. Our K being the constant that is changing. I mean, not our constant, is the variable that is being changed. These are our equations to find K, which is force divided by delta X. Our work is force times delta X. Our power is work divided by time. And our momentum is mass times velocity. Our reference point is the ground where it is 0. That is why there's no gravitational potential energy on the car. This is our work page. These are each of our variables that we needed to find. K is 0.0156. Our change in our displacement is 7.863 meters. Our mass is 0.1926 kilograms. Our velocity is 1.649 meters per second. Our force is 0.1227 newtons. Our time is 4.7295 seconds. And our acceleration is 0.6371 meters per second squared. This is our equation that found K, which is the variable that we are trying to find. As you can see, once I multiplied these out, I subtracted this from this, and then I moved the multiply by 2 and divide by 7.863. Our K after the car is launched is negative 0.051 due to its release and its uncoiling. Our work is 0.1227 times 7.863, which equals 0.0156 joules. Our power is 0.1056 divided by 4.7295, and that has 0.00329 watts. Our momentum is 0.1926 times 1.64905, and that is 0.3176. Real-world examples.
Pinball machine. When the player pulls the lever on the pinball machine, the spring engages and coils tighter, having maximum potential energy. When the player releases the lever, the spring uncoils and kinetic energy is exerted.
Another real-world example is a pogo stick. As the jumper puts down weight on the pogo stick, the spring on the pogo becomes ready for launching. With all potential energy, when the jumper then pushes off of the stick, it transfers into kinetic energy and still some potential.
And that's the end. Thank you.